Okay, so this proof is this is just a video basically for my analysis one students. Of course, anyone can watch it. I just wasn't happy with the way I explained the proof in the tutorial, so I've decided to make this video where I thought I could make myself slightly more clear. Uh, it's Friday evening after all. Okay, so theorem. I'm going to do this in painstaking detail. And for my students, well, you probably already know that the alternative write-up is attached to this email. So let xd be a metric space. Then what? For any subset E, which is contained in X, the boundary of E is equal to the closure, but we set complement out the interior. So probably I should remind you of some of the definitions, although of course you've all been studying hard and so you've memorized them and don't need me to because you went home and made flashcards right after tutorial, like I suggested, obviously. So, well, I'll just remind you of this one at least, that the boundary, the way we're defining the boundary, is it is all those points in X such that for all epsilon greater than 0, the epsilon ball around X has non-trivial intersection with E, and the epsilon ball around X has non-trivial intersection with the complement of E. Right. Okay. So time to prove the theorem. So proof. Okay. Well, we're going to begin in 2 steps. So first, we prove that we're going to prove that the boundary, as defined above, is a subset of the closure less the interior. Okay, well, how are we going to do that? Well, basically, that means that I need to show that, I need to show that everything in the boundary is contained in this thing on the right. So always my proofs begin with let something be in the set on the left. Okay, so let X be in the boundary of E. So what do we need to show? I need to show you that I first need to convince you that X is in the closure of E, and I will need to convince you that it is also not in the interior. So first, I'm going to convince you that it's in the closure. So either X is in E or it's not. Okay. It's a nice thing about the sets here. One is true or the other. Okay. So case one. What do we say? Well, case one will be if X is in E, well, then that means that X is in E union E prime, but that is exactly what E closure is. And so we're done. That case, very easy, easy to take care of. Case two is going to be a little bit more involved. We're going to have to exploit the properties of the sets that we have, right? So remember, we're working under this assumption that X is in the boundary of E. So probably that will have to come into play. And so if we scroll up, right, remember the boundary of E says something that, oh, for all epsilon, this happens and this happens. So probably we're going to have to, choose an epsilon at some point and use that to our advantage. Okay, so case two. Suppose that x is not in E. So we're going to use this. We're actually going to show that this means that E is in E prime. It's in the set of limit points. And that'll allow us to see that it's in the closure of E. So, well, how do we show something that's a limit point? Maybe I'll remind you of that definition as well. So the set of limit points of E, of course, is all x in X such that for all, do we want such that for all epsilon greater than 0, the epsilon ball around X intersect E minus X is non-empty, right? So we want to say that all the epsilon balls contain some part of X other than some part of E other than X itself, right? So suppose X is not in there. In order to show that, right, I need to show something about an arbitrary epsilon greater than 0, right? So I'm going to let epsilon be greater than 0. Now, what can I say about epsilons that are greater than 0? Well, since we're working under the assumption that X is in the boundary of E, remember the boundary of E tells me something about all of these epsilon. In particular, it tells me that the epsilon, that's a terrible B, the epsilon ball around X intersect E has to be non-empty, right? That's one of the two conditions. So choose, now that we know that that's non-empty, choose some element Y to be in the intersection of these sets. And assume, for the sake of contradiction, so assume to the contrary, I'll use abbreviations. Don't do that in your homework. I'm doing this because I've already spent a lot of time explaining this in class. So choose epsilon to be in this intersection. Assume, for the sake of contradiction, that y is equal to epsilon. Well, that's a problem because then that means that x is equal to y, and y we know has to be an E because it's in this intersection. But remember, we're assuming that x was not in E, right? So contrary, okay, it's like a one-step contradiction proof, but I just wanted to be brutally formal because I was, maybe too unclear in class. So now I'm going to be brutally precise. Contrary to our assumption, that X was not in E, right? So where was the problematic part of the assumption, though? Yes, it was assuming that y had to be equal to x, right? Assume for the sake of contradiction that y was equal to x. So hence it must be that y is not equal to x, and thus, what can I say? Well, I can say that in fact I have the stronger statement. Remember, we're trying to say that x is a limit point, right? So the whole point of that little excursion there was to say that actually I could remove x from this set, right? Because I know that y itself is different from x. So y is in the epsilon ball around x intersect E without x, right? In other words, the epsilon ball around X intersect E minus the set just containing X is non-empty. Therefore, or we could even say, we could even say by our arbitrary choice of epsilon greater than 0, we see that X is in fact it is a limit point. It's in E prime, which of course is a subset of the closure of E. Okay. So what we just did is we just wrapped up we had two cases, X was in E or X was not in E, and we showed that in either case, it had to be that X was in the closure of E, right? And that's one part of what we want. We started with the assumption that X is in the boundary of E. We've shown that X is in the closure of E, but we still, in order to finish off this direction, we need to convince the reader that X is not in the interior of E, right? So thus, in any case, X is in E bar. Okay, now you're probably not going to believe me based on what I'm about to write, but not every proof in analysis is a proof by contradiction, um, which may seem crazy, but anyways, here's evidence against that. Assume to the contrary that X is in the interior of E. Okay. Now we need to figure out why that is a problem. Well, again, probably we're going to have to do some stuff about these epsilon balls around X. And we know something about being in the interior of E, right? Being in the interior of E, I guess I'm slowly telling you all the definitions anyways, even though you've already memorized them, working hard with your flashcards on a Friday night. The interior of E, this is all the X in E. You could say X in X, actually. All the X in E, such that there exists an epsilon greater than 0, so that the epsilon ball around X is contained in E. But we're contradicting this, right? Like we want to show. So let me. Right, there exists an epsilon. So what I want to do is show you basically to convince you that I have this element is not in the interior. Well, basically I need to show you that for all epsilon greater than 0, this does not happen, right? Yeah, but we've assumed for the sake of contradiction that X is in the interior, so that means I can choose an epsilon, which makes this set inclusion hold. So thus we can choose epsilon greater than 0 such that the epsilon ball around X is completely contained in E. But that's a problem. But this would imply that the intersection of this epsilon ball with the complement of E, because it's totally contained in E, the intersection with the complement of E would have to be empty, but that contradicts one of our assumptions, contrary to our assumption, that x was in the boundary of E, right? Because at the beginning of this whole thing, we assumed that x was in the boundary of E, and that means for all epsilon, this epsilon ball intersected with the complement of E would have to be non-empty, right? But this claim here contradicts that, right? And where did that contradiction come from? Well, it came from supposing that X was in the interior, right? So hence, X is not in the interior. So just to wrap this up, thus we've shown that for any x in the boundary of E, x is in the closure of E, and it is not in the interior of E. So that's half the battle. We're halfway through this proof, right? So we've shown one step of the containment. Now we want to suppose we got to do basically the whole proof backwards. We got to suppose that E is in the closure of E and not in the interior, and we want to convince the reader that E is in the boundary of E. Sorry, X is in the boundary of E. I'll probably misspeak, but hopefully I'll be writing everything correctly on the whiteboard. So, say thus X is in the closure of E, and X is not in the interior. Okay, well, what do I have to show? Let me scroll up again. Hopefully you're not getting too dizzy. Depends on what you do on your Friday nights and how you pair that with math. So we have the we're trying to show that X is in the boundary of E, right? So what do I need to do? I need to show you for all epsilon, some things happen, that these intersections are not equal. So in order to do a for all proof, I need to toss in a let, right? Let epsilon be bigger than 0, and I need to convince you of some stuff. Well, I'm going to get one easy one, relatively speaking, out of the way. So since X is not in the interior of E, it must be that the epsilon ball around X intersect the complement of E is non-empty, right? Because otherwise, if that was empty, the epsilon ball would be completely contained in E, but then that would mean that we found an epsilon such that the epsilon ball is totally contained in E, but that would mean that X is in the interior, right? And we just said it's not. Okay, so you could probably fault me for not giving enough explanation on that part. I said it in words. I didn't write it down. Okay. So, well, who cares? Well, again, we're trying to convince the reader that X is in the boundary of E. So we've just verified one of these conditions. Now we need to verify the second of this condition. And again, we're basically going to do this by splitting it into the two sort of obvious cases, or well, maybe it's not obvious, but obvious is a dangerous word in mathematics, and you should avoid it at all cost, even if other authors do. Or I should say, even if other authors do not avoid it. So there's two cases. Either X is in E, or X is not in E. Familiar. So case one, suppose that X is in E, then, then X is definitely in the epsilon ball around X, and it's in E, so it's in the intersection. So that's the easy case. Hence, the intersection of these two is non-empty, and thus X is in. I guess actually we're not we're not quite done yet. So I'll just say that in this case before I conclude that part. Yeah. So the point is that in either case we want to be able to conclude that this holds. So now I'll do case two. Actually, case two isn't much harder. But so suppose, or I've used suppose too many times. I want to keep my writing fresh. Assume. Ooh, so exciting. Such a fresh new way to write this. Assume that X is not in E. Well, since we did assume that X was in the closure, and the closure is the union of E and E prime, well, the only way that it could then, if we're assuming that X is not in E and it is in the closure, it must be that X is in E prime, right? Okay. But limit points. We've got this floating this epsilon up here that we chose a while ago, and limit points. We know we can say something about that. Well, let's see. Have I said thus in a while? Thus, the epsilon ball around here with X E minus X is non-empty, right? So that's because X is a limit point. And so in particular, well, if I add something to one of these intersections, that's not going to make it any less empty. So we conclude that this is non-empty. Okay, so hence, we just wrapped up in both cases showing what we want. So we should say hence, in either case, this intersection is non-empty. So by our arbitrary choice of epsilon greater than 0, we conclude that X was in the boundary, right? And perhaps even, well, I think in the document I include and a little bit more words about that. But that is basically the end of the proof, right? Because this was the second direction. And what did we do? We started with the assumption that X was in E, the closure of E, less the interior, and we got down to the conclusion that X is in the boundary. So that concludes the second half. Hopefully that was a better explanation, or more clear, had a little more details in it. So